Hi, this unit is going to be on something I'm calling mutual information co-training. And I'm going to define this at an abstract mathematical level, but before I do that, I'm going to motivate it by the problem of language learning. So when children hear language, that the utterances, the language is in some context, some situation. So there's really two signals going on. There's the sound and there's an image or a situation that they're embedded in. And David Harwith, a few years ago, 2016, did this really fascinating experiment where he took a bunch of images and he had people describe them. Turkers described the images. And then he took the sound wave of the description together with the image and tried to build a system that could align the sound with the image. So this is a situation where we have two continuous objects, the sound wave and the image, and we're looking for what's in common between them. So you can think of this as a kind of multimodal learning. So let's see what kind of results he got. This is an image, figure from his paper. So what's going on here is there's a sound wave. The sound wave is describing this image. This is, so I'm going to read the sound wave. This is a picture of a girl standing in front of a lighthouse. The girl's wearing blue print dress. She has blonde hair and blue eyes. So as we go through this sound wave, the system is just trained now on pairs of images and sound waves. And the system has found some algorithm for aligning positions in the sound wave with pixels in the image. So this is a picture of a girl. So that's this red blob here is a segment of sound wave. This segment of sound wave has been identified with this set of pixels in the image. In front of a lighthouse, so this is a segment of the sound wave. This segment of the sound wave has been identified with this set of pixels in the image. The little girls, now we move over here to this one. So this time the girl got identified with these pixels, the word girl, presumably, wearing a blue print dress. So these two, this segment is aligned with this set of pixels. It's also picking up these. And then we have when the utterance hair comes on, we've got this set of pixels. So it's near the hair. And blue eyes. Now the word blue gets identified with blue things, not eye things. And then it goes on. Anyway, you see what's happening. Now, children eventually will map this sound wave to language, to a completely discrete representation, right? So maybe that comes on later. Or maybe the discrete representation emerges just from pure unsupervised learning on the sound wave via some VAE-like learning. But here, the focus here is on finding the mutual information, what's in common between the images and the sound wave. And we're going to formulate that formally as a mutual information learning objective. So we're about to do that. I'm about to do the formal treatment, abstract treatment. This abstract treatment was not explicitly followed by Harwith. So this is sort of a rationalization. So we're going to consider a population distribution on pairs, X, Y. And I want you to think of X as the image and Y as the sound wave. So these are both very high entropy, lots of bits in the picture and lots of bits in the sound wave. Your picture file is going to be big, your sound wave file is going to be big. Now we're interested in extracting, in this abstract setting, we're interested in abstracting representations of the image and representations of the sound wave, such that these two representations are capturing the mutual information between these two high entropy objects. So the example I'm going to use, because ultimately the children do map sound waves to symbolic representations. So I'm going to just, as an example, think about mapping both the image and the sound wave to a symbolic representation. We don't really know what the representation of images is, how symbolic it is. In a VQ-VAE, we are introducing symbols and getting a discrete, somewhat symbolic representation of images. So we don't know if images are represented in terms of recognition of the semantic categories or some kind of semantic labelings of the objects in the image. Anyway, I want to think about this example where X is an image, Y is an image, and we're extracting bag of word representations of both. So here's the formal definition. We got a population distribution on these pairs of high entropy pairs, multimodal pairs, sound and audio. We're going to introduce the two discrete latent variables, one extracted from the X and one extracted from Y, and they're going to be extracted by models that we're going to learn. We're going to learn a model that takes an image to a bag of words, say, and a model that takes a sound wave to a bag of words, say. And our objective, but I want to separate the example from the abstract representation. The abstract representation is just that we've got a population distribution on XY pairs. And we're going to learn two of these models. And the model objective is to maximize the mutual information between the two abstract representations while limiting the amount of information in each of them. And I'll talk about that again in a moment. So this is the formal abstract definition of mutual information co-training that I'm at least formulating here. So if we didn't limit the amount of information in X and Y, there's a trivial solution of maximizing this mutual information, which is just to set ZX to X and ZY to Y, right? And that preserves all of the mutual information between X and Y. And by the data processing inequality, this can never be greater than the mutual information between X and Y because we've lost information in abstracting it to some more compact representation. So this term will eliminate this kind of trivial solution. So it's a fairly important term. Now, another thing to think about is that this objective does not try to model the distribution on X and Y, right? A VAE is fundamentally trying to explain the continuous signal in terms of some latent variable, but it's critically modeling the distribution on the images given the latent variables, in terms of the latent variables. Here we've stopped doing that. We're not modeling the distribution on images or the distribution on sound waves. So this is somewhat analogous to a classification problem. In a classification problem, you've got X and Y as a label derived from X. And we do a conditional cross entropy that looks at the conditional probability of the label given the input X, right? So when we do our conditional cross entropy objective, that objective is looking at the distribution of Y given X, and it does not try to model X. Here, we're looking at the distribution of these labels for the two inputs, X and Y, and we're not trying to model X and Y. And that's important because X and Y are super high entropy things. And if we can reduce that to modeling much lower entropy things, the symbolic representations, the job is going to be easier, we hope. That's the hope. So that's a big difference. We're no longer modeling distributions on X and Y. So now I'm just going to go through a massaging of this, this expression. The problem we have here is that this optimization is on these entropies, and these entropies are defined in terms of the population, right? I'm defining the distribution on X, Y, ZX, and ZY in terms of the population. I'm drawing X and Y from the population, and then drawing ZX and ZY from the model's extraction of ZX and ZY from X and Y. But still, this mutual information is defined in terms of the population. So I've written the population as a subscript to emphasize the fact that these entropies are depending on the population. So the first thing I'm going to do is just replace this mutual information with a difference of entropies. So the mutual information can be written as in various information theoretic ways. In particular, I can write this mutual information as the entropy of Zx minus the entropy of Zx given Zy. That's a standard way of representing mutual information. But that breaks the symmetry between X and Y, right? It's saying I'm going to model Zx in this expression. I could also model Zy. So what I've done in these equations is just do both. So this is the mutual information. So this is 1/2 the mutual information plus 1/2 the other way of writing the mutual information. And so the sum of those two is the mutual information. So I've just replaced this mutual information with a mixture of the two ways of breaking it down into entropies. Okay, so then I can take this expression and just write it this way, because I'm subtracting these entropies here, beta times these entropies. So if I multiply this whole thing by 2 and then combine this term with the entropies up here, I write it this way. Okay, now I pointed out that all of these entropies depend on the population. So now I've written it in terms of entropies, either marginal entropies or conditional entropies. Now, the cross entropy objective is an upper bound on the population entropy. So when we apply the cross entropy objective, we're modeling the population with an upper bound on the entropy given by the cross entropy. And what we can do is just replace these population defined entropies by cross entropy upper bounds. Now we've got a problem here, and some of the entropies we're trying to maximize, and some of the entropies we're trying to minimize. Now, if we're trying to minimize entropies, that's exactly where the cross entropy is useful, because we get an upper bound and we're minimizing. So, let me skip ahead. What we can do is we can replace these terms with cross entropies, right? So now this population subscript has disappeared, right? So it's a cross entropy. So actually there is still a dependence on the population, but the dependence on the population is just, this is a cross entropy to a model. So I've replaced this entropy with this cross entropy that involves a new model. So one of these cross entropies is sampling from the population, but the quantity it's computing is completely defined by the model. So these are upper bounds on these original entropies, and that makes this a lower bound on the thing we're maximizing. Whenever you do variational optimization, you either maximize a lower bound approaching the thing that you're interested in, or you minimize an upper bound approaching the thing that you're interested in. So this is a step that, since we're maximizing, we can optimize a lower bound, and that's what we've done by replacing these entropies by cross entropies. Now, if we replace these by cross entropies, we don't have an upper bound or a lower bound, because we've replaced, we're trying to maximize these, and if I replace them by cross entropies, I've got an upper bound, and that's not what I want to do for maximization. However, if we think of the cross entropies as entropy estimates, then in practice, it might make sense to replace these entropies by computable entropy estimates, which were given by minimizing a cross entropy. So if I replace these by cross entropies, where we understand that these cross entropies are being minimized, then it could be a reasonable thing to do in practice. It becomes adversarial, right? The model is trying to maximize this quantity, whereas there's another piece of the model trying to minimize this cross entropy. So we've got a max-min situation, so it becomes adversarial, a game theoretic thing. But nonetheless, this could be quite effective. GANs, handle adversarial situations fairly well, do adversarial optimization fairly well. Carl Stratos has been working in this area, working with this objective, calls this a difference of entropies objective. It's very naive. It's just replacing the cross entropy with a difference of entropies and approximating the entropies with cross entropies. But sometimes simple, naive things work well. However, in the next unit, we're going to look at we're also going to look at the problem of maximizing mutual information, but we're going to look at a different approach, a contrastive, something called contrastive predictive coding. So we're going to do that in the next unit. So thank you.